Okay. So well done to everybody who has made it all the way to this lecture for the whole week. So I'm going to get to now the fourth part of the tools for string phenomenology. What we've done so far is, first of all, just motivating everything, why we should be looking at the problem of phenomenology in the context of, superstring compactifications or in a setting with some UV completion. Then in lecture 2, I made a point that the description in terms of Higgs bundles and their spectral data is sort of a very powerful tool. And so I think the actual sort of power of the approach only becomes sort of very clear once you understand it. For example, in this class of compactifications like F-theory on Calabi-Yau fourfolds, you can get sort of as a low energy description always something that's a Higgs bundle spectral cover description. So, this is like the local limit of some compactification of F-theory on an elliptic fourfold. And so today we'll get to the fourth question. So we started with why, how, and what exactly. And today we'll get to seriously. Are we actually just playing around with nice string theory, geometry, et cetera, or are we actually really trying to connect this to some physics? So that's actually what I would call sort of actually getting to the serious part of the problem. You could also say putting this into global models, having global compactifications, consistent fluxes. That's also sort of moving into making these into serious, well-defined, complete models. That's another way you can get concrete and serious about this. But today I'd actually really like to look at the phenomenological part. Okay, so there's lots of studies on this kind of models. Let me just recap what we sort of ended up with last time. So we said an elliptic fourfold compactification of F-theory with some fluxes switched on for an SU5 gut model. You can always bring it into this so-called Tate form, right? So that was an elliptic vibration that had very specific sort of coefficients, right? So x and y were the polynomials that were defining of the elliptic curve. If these b coefficients were just constants, that would just be an elliptic curve in C. And basically now our the general sort of story was that these things, if I look at elliptic vibrations that are Calabi-Yau fourfolds, these guys become now sections on the base of the elliptic vibration. And the Tate form is the general form you can get to, right? So in the sense that, if you have 7 branes wrapping the divisor in the base defined by z equals to 0, this is the form of this elliptic vibration. This will have automatically at z equals to 0 an SU5 singularity, and you can bring any Weierstrass form with an SU5 singularity into this form. Okay? So this is a nice geometric result. The way to connect that to the lecture 2, where we studied the Higgs bundle, was to take a local limit, namely we zoom into the vicinity of this divisor z equals to 0. So what technically we do is we look inside this geometry at a special divisor that we'll call the spectral divisor. So that's just defined by the vanishing of this combination here. That's a divisor in the geometry. Then we can ask, when we take a limit going to z equals to 0, close to this locus here, defining t equals y of x, taking sort of like a double scaling limit here, then this spectral divisor limits precisely to what we call the Higgs bundle spectral cover. And indeed, these coefficients were the coefficients in the spectral cover. And remember, they were parameterizing the eigenvalue data of the Higgs bundle. Okay, so in this sense, the Calabi-Yau geometry given by this Tate form is sort of really encoding the Higgs bundle data. And I think here you see very clearly that, for SU5, but also for SO10 or for E6 or for any kind of, gut group that you may anticipate, taking this local limit connects you back to the gauge theory, and you'll see what kind of things happen. For example, one of the newer developments is that, for example, if you have a U1, you get an additional section up here a local limit will give you a factored spectral cover. Vice versa is, by the way, not true. Okay, so now we'd actually like to do some phenomenology with this. And if you remember in the first lecture, we had a couple of sort of things that, gut model building has to address in order to be in any way sort of, taken seriously. So, and one of the ways we were going to, get around these things is have additional symmetries. So the first source of sort of despair in gut models is dimension 5 proton decay operators. This is Q cubed L operator. There are very stringent bounds on how much this operator has to be suppressed. A related issue is something that connects to the first lecture today, which is, have natural electric symmetry breaking in these Susy models. This so-called mu problem. So mu is this, superpotential coupling, which is the mass for the Higgsino, mu h up, h down. You would like to forbid this, or have at least some dynamical explanation why this is of some order of about 100 GeV to get natural electric symmetry breaking. The question is why. So usually you would like to forbid it and then have some dynamical mechanism to generate this coupling. And in fact, both of these problems are related. So if you look at the Yukawa couplings, they couple the HU to the 1010 and the HD to the 5 bar 10. And then you ask, so if I have a U1 symmetry that forbids this coupling, and I'll call these kinds of U1 symmetries U1 PQ symmetries. So the charge of the up and the down Higgs don't add up to 0, so that forbids this superpotential coupling. Then consistency with the Yukawa couplings, right? That HU and HD enter into the 10-10-5 and the 5x5x10 couplings implies automatically if this is forbidden, then in fact at tree level this also is forbidden, right? Just from the U1 charge assignments. So, you can sort of solve these two issues with one symmetry. Of course, you still need to make sure that then this lambda is large enough so that the dimension 5 proton decay is sufficiently suppressed, right? You could regenerate it from, other kinds of, higher dimensional operators. So this is really still something that you need to check. Okay, so in spectral covers, we said U1 symmetries came from a refinement of the spectral cover where you have a factorization. And one of the examples that we looked at was a 3+2 factorization. And that were explained, that realizes a U1 symmetry effectively that forbids the mu term, meaning it has precisely the property that the charge of up and down Higgses are non-vanishing. Okay, so this is like a model that realizes this type of symmetries. And so, in the local context, we can look at, all the matter, Yukawas, et cetera, and study these kinds of things. So that was sort of one thing. Yeah? U1 symmetries can forbid proton decay and also help us with natural electric symmetry breaking. There was another source of sort of despair that, usually you get exotics. And they can also be dangerous. For example, Higgs triplets can, couple and generate, again, proton decay type operators. There are also these kinds of exotics that come from breaking the gut gauge group SU5, for example, to the 321. Right? So you don't just get the gauge fields of the MSSM, but you also get these multiple heads. So both these and the Higgs triplets have to be somehow gotten rid of. So we haven't really talked about this yet at all, so we need to say what in this framework of F-theory compactifications are we going to do in order to resolve this. So there are, in string theory, apart from sort of just a standard field theoretic way of breaking the gut group, there are a couple of mechanisms. One is Wilson lines, so flat bundles, right? So it's very popular, in particular, in the heterotic context. So indeed, so Joe Marzano and Clemens, Pandak, and Rabi, they looked at this. And it's actually, a very limited class of places where you can find Wilson lines, which, you can then study and actually have a global model that extends these. The problem here is really, it's very limited. And I think an even bigger problem is there's sort of a theorem that you can sort of say straight away, just looking at the cohomologies for a flat bundle, you'll always get bulk exotics. So despite the fact that, Wilson lines are a nice mechanism, they are, first of all, not very general. So it's very contradictory to this initial approach that we wanted to be as generic as possible. And secondly, they have even a more stringent problem that the phenomenology is a little bit, you know, sub-ideal in the sense that they have actually bulky exotics. And so, you know, it's not the most promising framework at the moment. Maybe there are some ways around this. So I think this is worthwhile following up on. Anyway, so there's a second mechanism in F-theory that one can, you know, consider. And that's, in fact, much more in this line of thought that we would like to have something that doesn't sort of nail us down to a very specific compactification, but leaves us enough room to say general things about these class of models. And that's switching on so-called hypercharged flux. So this is not a flat bundle. This is actually switching on a U1 bundle in the hypercharged direction. And that is engineered in such a way that you move both these triplets, make these massive, as well as these, you know, XY bosons. And that's a very pretty generic construction independent of the surface S. So there's, however, you don't get this for free, right? So, you know, there's always something that you'll have to then take into account. So this hypercharged gut breaking comes actually with an additional requirement. And that will sort of become important when you want to embed these into, say, a base threefold and elliptic fibration over that. And so this comes from looking at this coupling here in F-theory written in terms of C4 wedge G4 wedge G4. So integrated over the Calabi-Yau fourfold. If you expand this, so we can, this is G4, so this is our G4 flux. I think I can expand this out. Now if I have a background U1 gauge field, right, so C1 of Ly, this will add to the expansion Fy plus this, you know, background field value, wedged into omega y, which is a 2 form that is sort of going in the direction of this U1, that's the hypercharge. And C4 is a Ramon bulk 4 form, so that's, again, I can expand it into 2 forms on the base B3. So the omega I are these expansion coefficients, and now if I plug this into this Chern-Simons coupling, I'll get a contribution only from this trace y ty squared, so generate a ty is traceless for the hypercharge trace ty squared gives a contribution times this integral, which is the integral of the background, you know, flux in the hypercharged direction, integrated over S by wedging it with this pulled back 2S of this class omega I. And then this term here is just C2 wedged Fy. So if I read this thing, if this is non-zero, this will actually give us a mass for the hypercharged gauge boson. Now that's definitely something that we would like to avoid, if possible. So there has to be some reason why this is either absent or this kind of mechanism is actually possible. So there's one very clever way which these people first initiated, not in an F-theory context, but in sort of local type 2B, I think, models, is to say, well, how about if we have a hypercharged flux background value where this integral here is vanishing? Right? So if this is actually 0, then there's no mass term generated for the hypercharged gauge boson, and this has to actually be satisfied for all the 2 forms in the base manifold. Okay? So what this means geometrically is this will be, you know, this C1 of Ly will be dual to some 2 cycle inside the gut surface, right? So the gut surface is this here. This will be dual to, say, some curves, say E1 and E2. Or E1 minus E2, so it could also be some connected thing. What this is saying is there's actually, if you embed this whole thing into B3, into the threefold base, there's a 3-chain that connects these. So there's a 3-chain of which the boundary is precisely this curve that's dual to this hypercharged flux. So this becomes a question, can you engineer such curves that are non-trivial in S gut, but become trivial, meaning there's a sort of, you know, 3-chain that ends on them once you embed them into B. And indeed, those actually, this sounds maybe more contrived than it is. This actually is a pretty sort of generic thing you can engineer in, you know, threefold bases. So it really, many now explicit examples for this. Okay, but this is a condition that you need to then satisfy when you embed that into the fourfold. Okay, but once that's satisfied, then this mass term disappears and the hypercharged gauge boson remains massless. So this gut breaking is up to this requirement that you have some condition on how you embed it into B3 is a very generic thing you can do, and definitely in the local models, it doesn't constrain the models. There's sort of a restriction then once you embed it. Okay, so now you can ask this sort of pretty clear question. So if I have U1 symmetries that forbids both the mu term and thereby also the proton decay dimension 5 operator in a local F-theory gut model with hypercharged gut flux breaking. So if I just ask this question here, I think most people would say, sure, why not? Why wouldn't it? And the interesting sort of answer is, okay, in local F-theory models, which is not yet even asking how is this embedded into some Calabi-Yau fourfold, the answer is actually no. So you cannot, in fact, have minimal SU5 supersymmetric guts with hypercharged flux breaking and have a U1 symmetry that forbids the proton decay operators. So how do you actually get about this result? So you can first of all classify all the possible U1 symmetries that you can have, meaning all the possible factorizations of the spectral cover. Yeah? So if you're looking at SU5 models, that's a very clearly defined question. What kind of factorizations are there? Which ones give rise to the right Yukawa couplings, the right matter content? So this is sort of a problem that's a classification thing. You can just do that. But then there's sort of this additional requirement. We actually would like to break the gut group with the hypercharged flux. So in fact, if you have these two things, U1 symmetries plus the hypercharged flux, then we can sort of always infer that there are non-gut exotic matter content in your theory. So you'll never have an SU5 minimal model. They're sort of, they're not the worst kind of exotics. They're like quasi-chiral, so they have under this U1 charge, they have this, the same charge, but there are still as, MSSM representations for this V2-1 group. There are like conjugates. And, they'll be charged under this U1, so there could be ways you could get around, having additional exotic light fields. But sort of the statement is, this small requirement, you would like to do U1 symmetries plus the hypercharged gut breaking, those two things don't work. So there is some question, why not? Right? And so first of all, this was observed, just looking at the local models and trying to build models, and you would always get additional stuff. So you wonder whether there's some underlying principle. And indeed, Joe then sat down and said, actually, that should really be coming from anomalies. And indeed, if you compute the GMSSM squared times U1 anomaly, so U1 is this additional U1 symmetry, actually this anomaly cancellation for any additional U1 will impose restrictions on the spectra. They're very general. So in fact, you can also generalize this. Aaron Pauli did recently calculation for U1Y, U1 squared anomalies, and you get additional conditions. So what I'll discuss is the implications of this first type of things, because they'll be particularly relevant for the kinds of models I'll discuss in a second. Okay, so these GMSSM times U1 mixed anomalies, they impose the following very simple equation, right? So you just compute these diagrams, and then you'll find this is the anomaly cancellation sort of requirement. So we have some U1 symmetry, and I haven't even said anything what the U1 symmetry is. Right? So let's go through this. What this is saying is all the 10 matter that you have, sum over these with the charge of this 10 representation under du1 times the restriction of the hypercharge onto that 10 matter. Right? So that's this combination. And that always has to be equated to the same sum now over the 5-bar representations. Right? So it's the charge of the U1 times the restriction of the hypercharge onto the 5-bar matter. That's a pretty simple sort of relation, right? But now let's look at the requirements that we wanted to sort of impose. Let's say assume we would like to have a minimal SU5 gut model, meaning there's only gut multiplets and nothing else. So then what you obtain from here is most of the things, the only sort of U1 that you actually can get from here, most of the things will come in gut multiplets, and the only contribution that actually enters into this equation non-trivially is the charge of the Higgs up and the charge of the Higgs down from here. And so if you don't want any gut, additional stuff that's non-gut, you will have the requirement that the charge of the Higgs up plus the charge of the Higgs down has to vanish. So this is just, saying phenomenology implies you will not have a U1PQ symmetry. But differently, if you would like to forbid this dimension 5 proton decay operator with, so the charge of the Higgs up, Higgs down can't vanish, then there's always something else in the equation that would have to cancel this non-zero contribution from the Higgses. Yeah? So, then once you impose this, so there's some non-zero contribution, then there will be sort of, given a U1 symmetry that has this requirement and it's a PQ type symmetry, you will have all kinds of additional multiplets. And so there'll be, like, as I said, sort of FF bar with, that are U1 charged. Okay, so this is from the anomalies, one of the implications. So, now you can really go in and say, cool, so I have a very well-defined setup. I have spectrocouple models. I'd like to have a U1 symmetry. What kind of, matter content can I get from this framework? So with a U1 PQ symmetry, we'll always get these additional sort of multiplets. So if you look at just a 10-10 bar and a 5 bar 5 representation, decompose that into the 3-2-1, then I can sort of label these degeneracies here, right? So this is always like the M would label the full gut multiplets, whereas the N's would label everything that's the offset from being a full gut multiplet. Similarly here, the K is telling us the 5 bar or 5 content, and the L is sort of telling us a deviation away from being full gut multiplets. Okay, so this is just a parameterization. Now I can ask, for spectrocouple models that have such U1 symmetries, what is the sort of class of models that we can actually get? And then also, given what the type of models is, what type of operator can still be generated that's Q cubed L times some suppression factor, right? And so this is really all the models that there are. So these are the requirements that n minus L is equal to 1, is 2, etc. So one thing that you will ask right away, which you didn't, but which probably you thought, is, hold on, so we're doing, the outset was unification in the MSSM, all the couplings will come together at about 10 to 16 GeV. So now you're adding into your spectrum stuff that's not gut. So clearly there's a disruption of unification. Yes, so if we have, just gut multiplets, the beta function running delta beta 1 up to delta beta 3 are just given in terms of the 10 multiplets and the 5 multiplets, right, which are M, let's see here, M and K, yes. So the M and the K contribution is here. But then there will be additional stuff now, which will be non-universal, right? So that will really tell us, how much we're going away from a full sort of, just a minimal gut scenario. So in particular, this non-sort of universality of these runnings will affect a little bit also, we'll see that, having these N and L will be quite important later on in actually building some interesting models. Anyway, at the first sort of look of it, this doesn't look like good news because, unification is not obviously preserved here. There's also another issue. So if you look at sort of, this non-trivial charge, so, this is like the offset from having, is there a question?
I thought they are vector-like with respect to the gut. So why does it modify the
But they're not full gut mod. They're vector-like with respect to the 3-to-1 group. Right, so there's 3 bar, but then here you will still get additional, for example, you just get doublets here and no triplets, for example. So it's not an SU5 full multiplet running, but it's, it really sees not the unification group multiplets, but actually SU3, SU2, U1. Okay? Okay, that's cool. Any other questions? Cool. So basically, if I sort of parameterize the offset from being, Q up, the charge of the Higgs out plus the charge of the Higgs down is equal to 0 by some singlet times delta, right? So this will be, some singlet could still generate this Q cubed L operator. So if it parameterizes in terms of some parameter delta, then delta is really something non-trivial. Now delta will actually enter into the type of operator that can still be allowed with this U1 charge assignment. So given one of these models, this delta, which is sort of n minus L, can still actually, produce 1 over lambda, x over lambda to the L, right? So if I, for example, couple this x to these FF bars, then this actually could pick up of f, and then x to the lambda to the delta. This stuff we would like to have hugely suppressed. On the other hand, this also measures actually how far we are away from, just having a running that's almost like a gut multiplet running. Right? So delta measures both the disruption from unification, but also it measures what type of operators are still allowed. And there's sort of a tension here, right? On the one hand, we would like to have this to be small. On the other hand, we'd like to have this, this actually, we'd like to have this to be small. And this thing here, actually, this is some scale that's, I don't know, lambda will be maybe 1 over m gut. And then this VEF will be presumably set by, say, 10 to the, 10 or 10 to 14 up until there. So this, we'd like to have this lambda to be, delta to be large so that we get a huge suppression here, okay? So there is sort of a tension between unification and the proton decay operators that we can still generate as higher dimensional operators. So in order to actually see that this unification is not a real problem, and also that we get enough suppression, we actually really need to look at the details of the RG in this context and actually see what are the contributions. Okay, but then still always check that we don't get any problems with dimension 5. So the combined RG for this problem is as follows. So we have, first of all, we'd like to sort of see how much do we deviate from the standard one-loop MSSM gut running, which are parameterized by this contribution here. So the alpha 3 at the weak scale will be differing by the standard sort of one-loop result by some delta. And this delta will get contributions both from standard corrections in 2 loops. So that's not anything that's special to our model. There'll be low-scale threshold corrections, and they'll be coming from the Susy spectrum, the particles that we'll be adding to our spectrum here will not all start running at one scale, but you could sort of define an effective scale M Susy from which you can model the running of all these particles, right? So, for example, there'll be a stop started to run earlier than all the other squarks. So all this can be modeled in terms of some one-scale M Susy that you can calculate once you have the Susy spectrum of the model. And then there are like 2 other contributions. So this is sort of standard stuff that phenomenologists would just add anyway. And then there are 2 other contributions which are not new in this model. So there are high-scale threshold corrections, which come from the fact that we have really a higher dimensional sort of theory. This is all embedded into some not just a field theoretic model, but we're actually looking at sort of a F theoretic completion. So there'll be KK modes actually on the S-gut surface. So this will give us additional corrections here, and we'll get the running from the exotics, right? So this will be the running parameterized by these 2 integers, L and N, which gave us this additional contributions that are non-gut. So putting all this together, you can then ask, is there sort of some parameter range, or is there even sort of any window where you can have consistency with the values of the gauge couplings at a weak scale? And the only parameters that are in the problem is sort of this delta from the high scale threshold corrections and this L minus N from the exotics. So this delta actually is something that will depend on the specifics of the surface S. But so in examples, this has been computed like for P2 and P1 times P1, one can sort of ask if this is of that order. So now you're getting into the range of where you're saying, okay, if this is sort of some order 1 contribution, then is there still a way that you can make this consistent with additional exotic states running with this specific kind of, parameterization in terms of L and N that come from the models that we studied. And the punchline is yes, so you treat this like a parameter and then try to see whether this becomes consistent in some choices of these parameters. And there's indeed some window that you can choose for this delta finite so that everything is actually consistent. It's not nice because this delta finite is something that you put in now, right? So at this moment, this is when I start relaxing and say, okay, I can't say the most general answer here, but let's assume this is a parameter that I can sort of slide, and then can this actually be made consistent? And we have some example values for this. Okay, but I think it's sort of not clear from the start out that adding these additional exotic states is something that can actually be made into something that's consistent at all. Okay, so this is sort of the additional stuff. This is the normal stuff we added together, and indeed there's sort of a window for that. Cool. So this is now the class of theories that we're looking at. And indeed, we can, for each of these L and N, make this at least modulo this delta finite consistent with the unification. Now, there's a question, what do we do with that? Okay, so these exotics, you could either say, I would give them a mass and they just disappear. Or you could say, well, maybe this is sort of the kind of thing that's interesting. Yeah? So nobody, in their right mind as a phenomenologist would just sit down and write down models which have this kind of a content, right? So this kind of exotic content coupled to an SU5 gut model. So, this is coming out of this class of theories, so you can ask, is there actually any phenomenological use for these? And so one question is there some way we could make, productive use of them? And I think sort of given that they're like vector-like from the point of view of the, say, 3-to-1 group, there actually is a very nice natural sort of way to make an application here is to use them actually as gauge mediation messenger fields. Again, there's a question, is that sort of something that can work? Yeah, so generalized messenger sectors have been looked at, but this is really not gut multiplets, but this is actually, just say additional doublets running as messenger fields. Okay, so before I get to that, we might have just a little bit of Susy Breaking 101. I think we had a nice lecture this morning, so I don't need to say too much about it, just that usually perhaps a lot of people will be looking at universal mass parameters for, say, gauge mediation or CMSSM, et cetera. Usually the most general thing is there's a soft Susy Breaking parameter space with about almost 200 parameters, and there needs to be some organizing principle. What is usually sort of discussed in the string theory literature is like two mechanisms. In fact, most of the time people look at a sort of, dynamical Susy Breaking in the context of you have some Susy Breaking sector, and you have the MSSM, and then there's some way to mediate the Susy Breaking. Yeah, so this is either done by gravity interactions or by gauge interactions. And most of the time for heterotic models, there's no way you could even isolate, right, the gauge interactions from the bulk physics. So there's really no reason to look at gauge mediation as sort of, a model of Susy Breaking. So a lot of focus is actually done in the regime of gravity mediation. What is possible here in this kind of, F-theoretic setting is you could really isolate the gut sector, say this is the 7th brane, then you have another cycle where you have some Susy Breaking, for example, generated by an instanton, and then there could be really sort of, matter fields that could mediate these two sectors, and then you could integrate out these gauge mediation fields and model gauge mediation this way. Okay, so this is what we're going to do. This is really a simplistic sort of way of writing this. So W is just the superpotential that we had so far, and now we're adding a Susy Breaking sector that's just sort of a primitive Poloni term. This could be much more refined, so this is what's happening on this side here. And this singlet here, this Susy Breaking field, will not couple to these two, quasi-chiral exotic fields. So F and F bar are normally your 5-5 bar or 10-10 bar messenger fields in SU5 gauge. So gut models with gauge mediation. Here, they'll actually be non-gut multiplets. Okay, so this sort of setup with a U1 charge, the singlet field here is charged under the U1, and this U1 will be of the type so that the Higgs up and Higgs down cannot couple to each other, right? So you don't generate a mu term. It's been actually discussed in the literature before by Ibe and Kitano, looking at high-scale gauge mediation models, forbidding the mu term with a PQ symmetry, and dynamically generating it from this non-renormalizable coupling. So it's very much like how in gravity mediation you generate the mu term, except that here it's really, the suppression here is by 1/m gut rather than Planck. And so X-Dagger now has to pick up a VAF to give mu of the order about 100 GeV. So Fx over m gut has to be around 100. So if Fx is 10 to the 19 GeV squared, you're about in the right ballpark. Okay, so this is a model that is, has been studied before in the literature, and actually is sort of something that in a very local scenario in F theory can also construct from, precisely a picture like this, where it's brain, an instanton wrapping here, and then the 7 brain with the gut group over here. Cool. So what happens actually now if these guys are non-gut messenger fields? So usually in gauge mediation, the gaugino masses, right, are coming with the beta function coefficient delta bi, and the two scalar masses also have this delta bi dependence, and normally these would just be given by these contributions from either tens or the contributions from the Ks, which are 5 bars. But now these are modified, as I said, right, so because we have additional multiplets labeled by this NNL. And now, so this will in particular change how the spectrum will look like. This is at a high scale. Now we can run these down and ask what kind of theories we get. Now before we do that, there's sort of one nice observation that usually there's a gaugino mass relation in 1 to 2 and 2 to 3 is 1 to 2 to 6. This gets now replaced, right, from this general expression here with the delta bi now given by this expression to a relation that's now non-universal, or doesn't satisfy this universal gaugino mass relation. So you get a dependence on the specific, messenger content of our theory, and more specifically, it'll depend also on these NNL coefficients, and so we can expect to see some difference from a standard, say, universal gaugino mass sort of setup when we look at these messenger sectors that are non-gut. Okay, so this is now really looking at just specific models that have the following feature, namely we would like to make these differences in the spectrum most prominent, right? So the idea is we don't want to model just what people have modeled before, but actually here this is a class of models which has really phenomenologically something that may actually be interesting, right? It's different from what you've looked at, say, in your Susy class on, gauge-mediated Susy breaking. So this is just a choice of these integers K, L, and N, and as I said, this is high scale, so gauge mediation, so the messenger scale, which is the mass of, of the messenger fields, is really almost sitting at the gut scale, right? So, and then one sort of useful thing is to compare this always to something that's a minimal gauge mediation, meaning just has gut multiplied. So for example, 300 without any non-gut content, right? So, and then just compare these things. Okay, so this is sort of a plot. I think the more interesting plot is over here. So what you do is, so lambda is fx over ms. We said fx is of order 10 to the 19, and ms is, listed here. So it's a very small range that you can sort of look at reasonably. The interesting thing here is this plot tells you the region of the Higgs mass. So the coloring is precisely sort of what ranges of Higgs mass we get, and we just about for very high values of lambda, go into the region of the about 126 or so Higgs mass, right? So this is, you see the line here is the line that comes from the left band, and here actually the small region that you have to the left is really pushed to the boundary with this value of the Higgs mass that's been measured now. Okay, so maybe a slightly more illuminating plot is this one here, where we plot the gluino mass against the Higgs mass, and so indeed for these models you can really reach this region of 126 or so. And this is one of these models with non-gut messenger sectors, but relatively high gluino mass. Yeah, so this is just to illustrate, okay, this is not something in this class of models. You can indeed be completely compatible with the choice, with the value of about 125, 126. Cool. So that's one thing. Now, another thing I was saying is we'd like to compare this to, say, the class of models that people have studied before, like minimal gauge mediation. And so one good way to compare these is to look at so-called models that have very similar, say, gluino mass and stop mass. So this sector here, you try to fit to be about the same to a minimal gauge mediation model, say with, this is the non-gut model, this is the minimal gauge mediation model. You try to fit these to about a similar sort of mass range. So then you can ask, what about the gaugino sector? We said earlier that the gauginos should have some, should be impacted by this non-gutness of the messengers. And indeed, you see it sort of just by looking at it that here, this is sort of slightly more squashed and this is slightly more broadened. That's in itself, okay, you might say, sure, there could be lots of models. How do I even distinguish these quantitatively, right? This is a minimal model, this is this. So, maybe there's another gauge mediation model with, gut multiplied messengers that would also give us something that looks actually much more like that in the gaugino sector. So to compare this, there's sort of a very nice method where you actually compute so-called kinetic edges. So you can look at this combination of masses, right? So here you have the neutralino 1, neutralino 2. So essentially you're measuring sort of, how the neutralino 1 and neutralino 2, which are sitting here and here, what the difference of these masses is. And so looking at this kinetic edge for, say, a minimal gauge mediation model with gut multiplied messengers versus this non-gut model, these are actually really distinct sort of values for this kinetic edge. So you can look at other things, they're much more similar, but this is a way you can systematically try to take two models that look almost the same and then still say, okay, the spectrum actually in the gaugino sector, for example, here is very distinct. Okay, so that's sort of one way that phenomenologists have tried to look at certain decay chains and then say, okay, if that happens, we can compute this kind of combination and then sort of say it's either this class of models or that class of models. So I'm not, this is just to demonstrate there's a crazy kind of model coming out of string theory, right? So we're sort of pushed into this. This is the class of models, right? So normally we would just say we wouldn't even look at this. But the point of this analysis is to say, okay, this is what we get. And it's a very general statement here, right? So we're not really looking at the Calabi-Yau X, compactification, fluxes, one specific model. Too bad it's not looking so interesting. This is really in F-theory with the C1 charge that forbids the mu term and the proton decay operator, hypercharge flux gut breaking. Then this is the class of models. So that's a pretty large class of models, right? This is, these are requirements that are very stringent, and this is sort of one way we can do gut breaking in this setup. In fact, the only really consistent way to do it in this context. So, you can then ask, this is really not just a random set of models, this is really what you would get phenomenologically in this context. And so the point of this analysis was, first of all, that it can still be okay with unification, and you could utilize these fields in a really sort of nice framework where you use them as gauge mediation messengers and analyze how they would differ from something that, you would just look at, if you hadn't gotten this motivation from string theory, meaning just standard minimal gauge mediation models. Okay, so that's sort of just to illustrate it. I'm not saying we should go out and search for these things. I'm just making the point here, you get models that make sense, and you can really distinguish them from stuff that's been studied so far. Okay, cool. So I think I have about 2 minutes left, so let me just summarize a little bit what we've sort of gotten up to. So there are a lot of more refinements in this whole sort of study of string phenomenology. We haven't really talked at all about flavor physics, and so there have been lots of claims about flavor physics. I think sort of at the moment the Madrid group, Fernando Marchesano and collaborators, Ibanez, have really tried to now make solid statements there, and I think that's that's very tough progress, but that's actually really sort of interesting results there. There are sort of lots of variations on this theme of F-theory compactifications, like you would add D3 branes. You can try to look at non-perturbative effects like instantons, D3 instantons, like for example, for the Susy Breaking sector, you're required to have that. Then sort of more formal questions you can ask is how do you actually write down the effective theory of F-theory that's been sort of pushed by the Munich and the Penn people to look at M-theory, F-theory duality, and then thereby derive the effective theory of F-theory. Maybe there are some more systematic ways of doing it using the intrinsic SL2R symmetry of F-theory. That's certainly something I think that would be interesting to develop. There are lots of, I think the last years have really seen a lot of development in the direction of global consistencies, global geometries and fluxes. How do we actually define these Calabi-Yau manifolds globally? Also, how do we actually find models that realize globally U1 symmetries? There's been really a lot of progress in that direction. So I think that's been the main focus recently. I think sort of the most important pressing short-term question here is what's sort of the dominant way you would break supersymmetry here. So I assumed in this toy model, right, this sort of just, we have these kinds of funny states. Let's use them as gauge mediation. There's really no underlying reason that I've brought up that says, gauge mediation can be a dominant contribution to Susy breaking. I think there should be really a systematic analysis of that in the context of F-theory in order to really make statements about is it gravity mediation or can gauge mediation actually also be a relevant contribution that really talks to understanding Kähler potentials, those for matter fields. One other question is, can you actually model natural Susy here? I think that turns out to be a little bit more difficult than you would think, but that would be interesting to understand, right? Is this framework sort of such that I can really distinguish between the third generation and the other ones? And then I think the more long-term direction of the whole field is, I think, to extend this systematic study, right? So I hope this has sort of come through, right? We are systematically trying to get from a local model with a Higgs bundle spectral cover description up to global models and then see what is the direct connection between them, right? So this is like, I think that's a really powerful way to approach this whole subject. I think there should be an extension, and a much more systematic extension of that in terms of M-theory and G2s, type 1 prime, and other frameworks, where you can also, start with some local description and then try to systematically include global aspects. Okay, so that's it. I think we should thank the organizers, which are sitting just down here, Neil and Boris, for a really cool conference, and it was cool actually, and let's thank them.
So we have time for some questions.
Yep.
Can you realize split supersymmetry in this model?
Yeah, so there's a little bit of, there are all kinds of tricks you can play. So in order to really distinguish sort of, certain, let me explain. So for natural sources, I actually have really looked at the problem, so I can maybe say a little bit concretely what the issue is. So what you could try to do is you could look at not matter coming just from curves, but like we discussed in the second lecture, I think, matter coming from actually the bulk, from S-gut, from zero modes on there. And then there's a question, can, for example, that give you, say, a lighter third generation than the first and second generations? But that really all talks to this problem here, that you don't know a lot about the Kähler potentials. So if you knew that, then I think you could argue something about, somehow these bulk modes will be, getting much lighter, soft masses than this first and second generation that I put on a matter curve. So there are lots of games you can play, but I don't think at the moment we have a very clear understanding about this. And in order to really do something that's a systematic study of Susy breaking, you will have to have some information about the Kähler potentials, right? So it's a fun question to address, also natural Susy, but I think it's something that has to really be addressed by a step forward, first asking, okay, what's actually even possible in these F-theory contexts, Kähler potentials for the matter, for the bulk modes, and then you can address this.
Actually, Sakura, I wanted to know, is it possible, if you take, for example, the examples that you just gave, is it possible to develop those to the extent that you could start to address the tension that Jan Judice was talking about?
Which tension?
Well, the tension
talked about
the
a lot
stuff
of
mass, right?
Yeah, so, I mean, these models will have a lot of fine-tuning. Sort of, I think he had this plot, right, where you have, so he could rule out, right, given Higgs mass, he could rule out very high-scale Susy breaking models. Here, this is also a high-scale Susy breaking model. This fx is like 10 to 19 GeV, so it's very high scale from the point of view of gauge mediation, right? So, but still, we can get quite nicely up above, even 126. So this Higgs mass versus the Gluino mass for these models. So, this is gauge mediation. There's going to be presumably a problem finding these models because everything is pretty heavy. Yes. So I'm not explaining, that's why I'm saying it would be nice if you could actually engineer models with inverted hierarchies, with light third generation, and then try to see whether, they have slightly more, accessible spectra. You see, this is all sitting quite high. So the stop is sitting here about 1.2 TeV, and then the Gluino is sitting above there, so 1.4 TeV. Right, that's the Gluino here. So these are very high-scale models, so you will not see a lot. So, main production is in the Gluino, so here is the Gluino production. This number 5 is the is a GMSB model, and then the 2 is the one, the lookalike model. So if you compare these, right, so this is for, I think, LHC14, this is for 7. Yeah, it's not a lot that you can get, because everything is extremely sitting up high. Yeah, so it's not addressing the question. So, in a way, these are standard minimal gauge mediated models, except that you will have a different, gaugino sector. That will be dominantly seeing the difference, right?